This is the presentation for our paper, a tree-structured multitask model recommender. In this work, we studied multitask learning, which aims to solve multiple tasks simultaneously. For example, we may want to tackle multiple vision tasks on one input image. Compared to independent models, multitask learning is an effective way to improve task performance while reducing computation and storage costs. A common practice of designing multitask models is to share the whole feature extractor, or we say backbone, across tasks, then feed into separate task-specific heads. However, oversharing information between tasks can cause task interference and accuracy degradation. Therefore, it becomes a major challenge to identify a good intermediate state between independent and overshared architectures, namely a partially shared architecture. Such a partially shared architecture is also called a tree-structured multitask model. A tree-structured multitask model usually shares shallow layers like tree roots and separate deeper ones gradually like tree branches. This figure shows three possible architectures for a set of three tasks and a backbone model with 5 layers. Here, the key challenge of identifying the best architecture is to decide where to branch out for each task. Some previous works manually decide the branching point. They adopt the simplest strategy of sharing the initial layers of a backbone model, after which all tasks branch out simultaneously. Such kind of methods call for domain expertise when tackling different tasks, and usually result in suboptimal solutions due to the enormous architecture space. To automate the architecture design, some works deduce the layer sharing possibility from well-trained independent models to build the multitask model. However, they ignore positive task interactions that could bring the potential generalization improvement. So the solutions are still suboptimal in terms of task performance. Some other works attempt to learn where to branch by introducing differentiable task-specific policy to optimize the best branching points together with the model weight. Those methods are usually hard to train because of the additional policies, and the learned architectures cannot guarantee to meet the user-defined computation budget, since this method are like a black box where users cannot control the exploring process. Therefore, to overcome the limitations of existing works, our idea is to build a tree-structured multitask model recommender, which consists of 3 components: a branching point detector, a design space enumerator, and a task accuracy estimator. Given an arbitrary backbone model, the branching point detector will automatically identify its sequential branching points without manual effort. Then, based on the given set of tasks and the identified branching points, the design space enumerator can explore all the multitask model candidates completely to identify the optimal solution. Finally, the task accuracy estimator is to predict the task performance of all the model candidates without performing actual model training. Those task performance plus other attributes such as model size and flops could be stored in a performance table to facilitate online queries. When deployed, the recommender takes a user-provided computation budget C as input and suggests multitask architectures by looking up the performance table on the fly. Then let's dive into the details of each component. Firstly, the branching point detector is used to partition the CN backbone into sequential computation blocks. It has 2 stages. The first stage leverages the graph card theorem to partition the original computation graph into candidate blocks. The second stage is to merge candidate blocks that contain only unparameterized layer and normalization layer with adjacent candidate blocks to generate final computation block, each corresponding to a viable branching point. Then the design space enumerator will enumerate the architecture candidates completely. We firstly formalize the architecture representation by a novel data structure called layout. Here is a 4-task model and its equivalent layout. Each node in the original model is represented by a task set, and each layer is a list of a task set. Then an operator called layout cut is designed to derive new multitask architectures. It can transform one layout to a new one by selecting a task set and dividing into two task sets. For example, we can cut the selected task set here into two sets to generate a new layout. Therefore, by recursively applying layout cuts on the initial layout and all the generated layout until no new layout is derived, we could enumerate all the candidates. Then, for each architecture candidate, the task accuracy estimator can predict its task accuracy without performing actual model training by leveraging well-trained two-task architectures to quantify task interactions. Given a three-task model, we can figure out its associated two-task models from all two-task combinations. Like for task 1 and 2, they branch out after the third block, which is corresponding to a two-task model in the right figure. Task 1 and 3 branch out after the second block, which is just the second two-task model. Tasks 2 and 3 branch out after the second block as well, which is the third two-task model. Therefore, we propose to estimate task 1's accuracy of the three-task model by averaging task 1's accuracy of the first and second two-task models. Then for task 2, its accuracy is the average of that of the first and third two-task models. And for task 3, we estimate its accuracy from the second and third two-task models. The final ranking score for this three-task model is calculated as the weighted sum of the task's accuracy. Here we use SVDE as a weight to capture the task accuracy variance when training two-task models. So tasks with higher accuracy variance will have lower weight in the ranking score. In the end, our performance table is built on the ranking scores of all candidates in the design space, and we can use it to recommend top architectures within the computation budget on the fly. Then comes to our experiments, which are conducted on two popular vision datasets in multitask learning, NYU-V2 and Tiny Taxonomy. The baselines include independent models, tree-structured multitask learning models, and general multitask learning methods. The multitask models are built on DeepLab ResNet 34 or MobileNet V2 with ASPP heads. This table shows the real task performance of the top 1 recommended architectures under different computation budgets. Our recommender could always recommend architectures with high task performance within the computation budget. Notice that when the budget is one model, the only architecture we can generate is the all-shared model, which suffers from accuracy degradation. And as mentioned before, the recommender can suggest top architectures on the fly without additional effort by simply filtering out architectures that do not satisfy the budget in the performance table. We also conduct experiments to evaluate the efficiency of the task accuracy estimator by calculating the Pearson correlation coefficient between the predicted architecture ranking and the Oracle ranking. The Oracle ranking is obtained by actual training multitask architectures in the third space. As shown in this table, our predicted ranking has a high correlation with the Oracle ranking, which demonstrates the reliability of the task accuracy estimator. Finally, we show the comparisons with SOTA multitask learning methods. Generally, the best multitask architecture suggested by our recommender could achieve competitive or even higher overall task performance. And when the computation cost is similar, our architecture can still achieve better task performance. In summary, in this paper, we propose a tree-structured multitask model recommender, which could automatically support various CN backbone, completely explore the design space, and faithfully estimate the task performance. The code is open source already. That concludes my presentation. Thank you for listening.